Perfect. Okay, so now let me start. You all see my screen? I think so. So today we are going to talk about how to do frame modeling in OpenSeas and STKO using the distributed plasticity approach. So the file that we are going to see today, let me just load the output so you can see the final result, and then I will show you step by step what we are going to do. So this one will be a very simple, let me create a fiber cross section, okay. It will be a very simple one bay, one story building. In the first model, we will just do a very basic modeling. So just 4 columns, 4 beams connected together. So just the columns. And we are going to see how to put nonlinearity through fiber cross sections. In the fiber cross-section editor that we have in STKO, you will see how to create automatic confinement. So you don't need to create both the unconfined and the confined concrete. The confined concrete will be automatically computed inside STKO. And then I will talk a little bit about one typical problem that arises when you use materials with strength softening, for example, concrete, in a distributed plasticity approach, which is the dependency of the solution on the mesh size. So we will talk about how to do fracture energy regularization. This is a kind of problem that you don't have in lumped plasticity approach. So when we are done with this first basic example, we'll start adding other features. For example, how to add nonlinear shear using the section aggregator in a second step. Then we will see the problem. Well, in the first model, we'll create, of course, the structural model plus the rigid body, the rigid diaphragm. As you may know, the rigid diaphragm creates a problem with fiber cross sections because it does not allow the enlargement of the beam, and so the beam can have a very large axial compression. So how to solve this problem? In this case, we can use an axial release, and I will show you in STKO how you can use the hinged beam compound element that will basically allow you to automatically create end releases for the beam. In this case, the axial end release. So we will see how to remove this problem, and then finally we will add another level of complexity, which is the nonlinear beam column joint. So you will see how to create interactions, how to create rigid links to simulate the panel zone, and how to add zero-length elements for the nonlinear spring of the joint. As I told you, to follow these examples, you need the latest version of STKO. You can download the trial version here. And if you want to follow the example that I will be doing, you can download them at the webinar support files. And then, of course, when the webinar will be done, we will upload the recording for this webinar. So let's first start with this basic model. So first of all, as I've been saying in all the previous webinars, in STKO and in OpenSeas, you don't have the concept of unit system. So you have to choose your unit system, and you have to be consistent. Now, in this example, we are going to use Newton and millimeters. Okay. So this is the interface that you have when you first open STKO. We are in the preprocessor now, and we are going to create this model. Perfect. So the first thing that we want to do is to create 4 base vertices from which we will extrude our model. Basically, the bay is 4 meters and the height is 3 meters. So I will put one node here at minus 2000, and then another one here, and once again here and here. Of course, you can enter the points by clicking on the grid, because I have here the grid snap, or you can type the coordinates in the terminal. It is the same. So in this case, we created 4 points, okay? Now we want to extrude them to create columns. Basically, the extrude command in STKO extrudes every kind of geometry. So a vertex will become a line will become a surface, and that surface will become a solid. Now in this case, we want to convert all these points into four columns. So I can click on the extrude command, and as you can see, I'm going to extrude them. Now I want to use the orthogonal constraint, so I can only extrude them in the orthogonal direction, and I can type 3000 here. Oh, let me do it again because my laptop here, extrude. It's always a problem when I use the remote desktop. Okay, so 3000. Right click and you're done. Now, as you can see, the base vertices are still selected, and now we can press cancel to delete them. Okay, so now we have four geometries. There are four simple lines. Now we want to create the four beams on the top, so we can use the lines command. We have the OSNAP constraint, so we can just move close to the OSNAP point, and we click. Okay, and then we close it. Perfect. So now we have four columns and one single polyline for the beams. Now in this first example, as I said, we want to create a model which is completely connected. The joints will be added later on. So sorry because I can hear someone else talking. If you don't mind, I will let me just mute someone else. Otherwise, we cannot hear. Okay, sorry. Perfect. Okay, so as I told you in this example, we are going to model everything in continuity. Later on, we will add discontinuity at the nodes to create the beam column joints. So if I want to merge all these geometries into a single one, they are all edges, so I can use the make wire command. The make wire basically converts all these edges that are connected through a vertex into a single polyline. So I select all of them, right click, and then I have just one single geometry. So all the edges are physically connected, while before they were only coinciding. Perfect, so now we have our geometry. Later on, I will show you how to orient the cross section and so on. Now let's assume that this geometry is fine for us now. The next thing you have to do is to start creating physical properties. So as I said, we're going to use the distributed approach with fiber cross section. So for fiber cross section, the first thing you have to do is to create uniaxial material models. So we can go in property, we can create physical properties. Physical properties means constituted models. It can be uniaxial models, 3D models, cross sections, and so on. So everything that defines the constituted behavior of a piece of geometry. So you can issue the commands either here or on the work tree. I personally prefer to work on the work tree. So let me add a new uniaxial material and call it concrete. We go on the model and we choose our model. So we go under material. We want to create a uniaxial material and a concrete material. In this case, we're going to use a simple concrete 0,1. Okay, and the parameters for this one is minus 33. We're working in megapascals now. Minus 0.002. Minus 5 as a residual stress. And minus 0.015 for the ultimate strain. Now, if we want to see how this parameter affect the shape of the constitutive model, we can use material tester. If you have seen the previous version, probably you can see how it works. So let's say I want to test it in a monotonic test using 1000 subdivisions, and I want to push it a little bit farther than the ultimate strain. So let's say 0.016. Let's test it. So this is how it looks like. If you want to do a cyclic test, for example, to see how it behaves, you can choose one of these cyclic protocols like this one, and let's use the peak strain here as the parameter. We don't want to test it on the positive side, only on the negative side. Let's test it. And this is how it behaves in a cyclic protocol. So let's say this material model is fine. Press OK. Next thing, we need to create a uniaxial concrete for rebars. So we go once again in Add. Let's call it Steel. We go under Model, Material, Uniaxial, Steel and Reinforcing Steel Materials, and we choose Steel 02. We're going to use 407 for the yield strength. And then we have some parameters to define the Menegotto-Pinto cyclic behavior. So 18.5, and then some standard parameters, 0.925, 0.15. I think we have a question here, just a second. Okay, sorry. And then in B, we may want to add some hardening, but in this case, we don't need any hardening, so this is fine. And the Young modulus, which is 206,000. Okay. Once again, we can test it to make sure that everything is fine. And it's better if you test all your models before running the analysis, because it can really help you to spot some issues that you may have. Okay, so let's say this one is fine for us. Now we have the two material models, the unconfined concrete and the steel. So we are ready to create the cross-section. As I told you, there is no need to do a manual calculation of a confined concrete, because as you will see, we have a procedure that automatically computes the confined concrete. I will show you. So now we're going to create the fiber cross-section for the columns. So let's call it column fiber. It is a cross-section, so we go under Model, Sections, and we don't choose the standard fiber, because fiber typically is used to create general shaped fiber cross-section. In this case, we just want a rectangular cross-section, so we can use this facility here, rectangular fiber section. And as you can see, you have some parameters to define the rectangular section. All the fibers will be created automatically for you. And you have one extra advantage. Here, STKO will compute automatically the confined concrete properties, starting from the unconfined ones and the reinforcing layout. Okay. So in this case, we want a 3D section. Let me just add the torsional constant, because we are going to do a 3D modeling and we need it. And it will be elastic in this case. So we add it in the cross section. The torsional constant in this case is 2.2E13. Torsional constant times the shear modulus. The cross section will be 500 and 300 with a cover of 20 millimeters. Then corner rebars, they are fine, one rebar for every corner. And then we want 3 rebars on top, 3 rebars on bottom, and just 2 rebars on the 2 sides, 2 and 2. As you can see, the drawing here updates accordingly. Then when you go under the materials, let me create some space here, okay? We want to select the rebar material, and we choose the steel, okay? As you can see, it gets the color of the steel you created before. And then you choose the concrete for the cover. When you choose the concrete for the cover, as you can see now, you didn't choose any material. So here we have a 0, meaning no material for the core. In this way, STKO understand that you want STKO to automatically calculate the confined version of the concrete. Now, this confined version depends on the shape, the unconfined cover, and the stirrup layout. So for example, let me change something in the stirrup. You will see that everything changes accordingly. So let me reduce the diameter. Let me reduce the spacing. Okay, so you will see the effect of the confinement decreases. The number of legs, let's say 2 and 2 in both directions. And this one is the strength of the steel model that we use for the rebars. Now, in this case, we put the same 487 that we are using for the longitudinal rebars. Okay, and then if you want, you can also change the confined model. Like here, we're using Mendel or Eurocode and so on. For the moment, let's choose Mender and let's choose the William Rankle surface for the computational lateral pressure. So as you can see here, you have a quite nice facility. This facility has been developed by Dr. Diego Talledo, and it is an example of how you can customize STKO just by using the Python scripts. All this stuff here was not coded inside STKO in the C++ code of STKO. It was just added as a plugin from a user, which is Dr. Diego Talledo. So as you can see, if you know how to program in Python and you know how the STKO Python APIs works, you can do your own customization. Like this one is very useful. So you can press OK, and now we have the fiber cross-section for the columns. We are not going to add directly the fiber cross-section to the elements because we need one extra step. Typically, when you do a solid model, it is fine to take a material and drag and drop it to the geometry. But for a beam, it is a little bit different. You don't need only a material. You also need the integration scheme, because in OpenCV you have many integration schemes for the beam. So that's why we need this extra step. So we go under physical property, and we call this one column property. We go under model, special purpose, beam column, and we choose the beam section property. The beam section property basically allows you to choose the integration type that you want. For each integration type, you can choose the actual integration scheme. And then, according to the integration scheme, these other things will change. For example, in this way, we are using the standard Robato integration scheme. But for example, if you want to replicate the beam with hinges model of Professor Scott, you can go under hinges, and you can choose, for example, hinge radau, and here you can put a section for the two end hinges, the plastic length, and the elastic section in the middle. But for this example, we are fine with standard integration scheme and Lobato. So we choose 5 integration point, and in all integration point, we want the fiber cross section. So in this first example, we are just going to account for PMM interaction, not shear, and torsion is considered elastic. So press OK. Now we can assign this material model to the geometry. Now, as you can see here, if I select this entire geometry and I drag and drop this one, I will assign this property to the entire geometry. This is not what I want. So let me press Ctrl Z. I want to assign these ones only to the columns. So how do I do this if I have only one geometry? You have two options. One is to expand the node in the work tree. You go under edges and you can select only one edge at a time, and the edge that you want for the selection. Now, in this case, they are the columns. Otherwise, if you don't want to use this worksheet, but you want to use the graphic window, you can have a look at these points. If you go on the user manual, you can see all these buttons and what they mean. For example, this one means I want to select vertices. This one, I want to select edges. Then I want to select faces, solids. And then there is this button here. This one means I want to select the entire geometry. So if I switch it off, it means I don't want to select the entire geometry. I want to select this kind of subshapes. As you can see now, I can select the sub-items of the geometry one by one. So let me select all the columns. And now that I have this selection, I can drag and drop this one. Okay? So now I have my columns assigned. Now let's say, for example, that now you have seen how to do the model, how to do constitutive modeling, and how to assign them. Now let's assume that for some reason, columns in the model that you want to simulate are not oriented in this direction, but in the opposite direction. So how do you change it? You can either change it here, but it is not convenient. Otherwise, you can change the local axis of the geometry, which basically will be reflected in what is known in OpenCV as coordinate transformation. So how do we do this? First of all, you can see what is the default local axis by switching on this button here. So here you can see the default local axis that STKO has assigned to the geometries. In this case, the y-axis is pointing according to the global y-axis, while we want to make it point along the global x direction. So how do I do this? I can go under local axis here. I can create a new one, add. When you add a new local axis, you can choose the type of local axis that can be a rectangular, a cylindrical coordinate system, or a spherical one. Now let's say that 99% of the cases you are fine with the rectangular one, as in this case. Let's call it column orientation. Let's press OK. And let's see, STKO say, okay, specify the first point, the origin for the local axis. Any point, like this one, for example. And then we want to make the y-axis point along the global y-axis. So like the global x-axis. Okay, just a second, let me mute some user because otherwise we cannot hear anything. Okay, sorry. Perfect. Okay, now I created this local axis. We need an extra point, fine, perfect. Now we need to assign it. How do we assign it? As I told you before, so let me select once again all the columns. And then I drag and drop this local axis. As you can see now, the columns are rotated. Okay, so in this way you can create your custom orientation. And as you can see here, now the color of this local axis is not grayed out like this one, meaning that those ones are the default ones, while these ones are the user-defined ones. Okay, so whenever you want to change the local axis of the geometry, it is sufficient to rotate this local axis. Okay, so now one extra thing that you have learned is how to orient cross-section in STKO. Perfect. So now we are fine with this. We can switch off the visualization of local axis. We don't need it anymore. Now we are going to do the same that we have done for the columns, but for the beams. Now we can, the beams, let's say for simplicity, we are going to use the same cross-section, but without the confinement. So how do you do this? You can clone the column fiber. So right-click clone, and then we can edit it to change some parameters. Let's call it beam fiber. And then it will be the same with some small change in the layout, in the reinforcement layout. We will have only, this is fine, the geometry is fine. I will put 0 reinforcement on the lateral sides, only top and bottom. And we will use only 2 in the middle, 2 in the bottom, 2 in the top. Okay? And we don't want to use the confined concrete here. So how do you, for example, let's say you don't want to use the automatically confined of STKO. Well, you can just specify your concrete model in the core. So if you specify your concrete model, STKO say, okay, you take care of the core material. We don't do any calculation. Perfect. So this is the cross section for our beam. Once again, we need to use a section property, so we can clone it because it will be pretty similar to this one. So let's edit it, call it beam property. And of course, we need to change the section tag. We move from the column to the beam one. We are still fine with a Lobato integration scheme and 5 integration points, so press OK. We select all the beams, and we can drag and drop it. Okay, so we are fine also with the cross section for the beam. Now we are done with the physical properties. We need to go on and work with the element properties. Basically, in element, as I said, in physical properties, you define the constitutive behavior of your model. While in the element property, you define the kinematics, so the finite element formulation. Now, in this case, we just need one single element type for the entire model, which will be the three-dimensional force-based beam column. So we go under element property, we click add. Let's call it beam element. beam element. We go under model, beam column elements, and we choose the force-based column. We are in 3D, and we want to use a linear kinematic. As you can see here, the transformation type, you can choose between linear, p delta, or rotational. And this one will be used to create the coordinate transformation command that is available in OpenSys. So you may ask, why don't you ask me for the z vector? Because we take it from the local axis. So in this
on the rotation distance to floor, that'd be great. Have a card on file or? Okay, okay. So it's a Visa and the number is 4147 420 390 182 12. 603. It's about. That's it. No. All right, bye.
So now we have the basic response, the refined response regularized. Okay, now we're going to add shear to see what changes in my model. Okay. Oh, by the way, let me show you something. This is the fiber cross section. Let me create another plot group. Let me show you the Gauss points. So typically you can choose the Gauss point when you want to visualize the results on the integration point. Like in this case, for example, we want to visualize what's going on in the beams and the columns. So let's choose, for example, deformation. So if you want to see where is the strain localization, you can choose the curvature. And this is the second stage, the other one probably. Yes, is this one, the localization in this direction. You can go on in the right, so you can see at the beginning there is a linear curvature like this, and then when there is strain localization, the entire curvature goes into a single Gauss point representing the plastic hinge. Now, what is interesting to see now is that if you go on the Gauss point plot and you see section deformation here, you only have epsilon, the two curvatures, and theta for the torsion. You don't have any response in the shear. Why? Because we didn't we didn't include it. So let me just need to. Okay, sorry for that, but we couldn't hear. Okay, so as you can see here, the shear components are missing because we didn't include it. This is obvious in OpenC. So we go back to our preprocessor and we want to include shear. So how do we include it? So the first thing is to define two uniaxial material models for the shear. Now we're going to add two different material models for shear in Y and X direction. Now remember that Y is the strong direction in the beam here. YZ is the weak direction. So let's go in physical properties and create another uniaxial material model, and let's call it column shear in Y. Y is the strong direction, but actually I just realized that I made a mistake. I put in the file that I sent you, that you can find in the website, in the material model for the strong direction, I put the input values for the weak direction and vice versa for the other one. But it is not important, but if you want, you can swap them. Now I go under material, uniaxial, and I go under, for this kind of model, I choose the modified cap Ibarra Medina Kravlinker, so uniaxial, other uniaxial material, and the pinching one. Okay. So let me put some values here. Now keep in mind, when you are defining the shear, it's not like the concrete here that should be in stress versus strain. Now in this case, it should be the total shear force versus the shear strain, because we don't have a fiber cross section that defines the shear area. So we have to include the shear area inside this Costello model. So the stiffness for this one will be 5.01 e to the power of 9. Then we have some values here, like 0.00197. Same thing. These are strain hardening ratios. Then we have the initial strength is 187,000. Okay, same for the negative part, but with a negative sign. Then we have some factors for the cyclic behavior, but it is not important here. So let me just put those values. 0.4, 0.4, 0.1, then all those zeros. Then let me define the plastic. Well, here are called theta because typically this model is used for moment rotation, but in this case we use it for shear strain. So look at these as shear deformations. So this one would be 1 to the minus 3. Same the other one. Then 1 to the minus 1. Same for this. And same thing for the residual stresses. It will be 0.1 of the total of the strength. And then the ultimate shear strain will be just a large value, let's say 1. I don't want to make this model drop to 0. So let's put it 1. And let's see how it behaves First in the monotonic behavior, let's push it up to the ultimate shear strain, which is 0.1, a little bit more. Okay, this is the behavior. So you have a first elastic stage, then a small hardening, then you reach this peak. If you're interested, we just use this formula here for defining the shear strength, but you can use whatever formula you want. And we are done. And to see the cyclic behavior as I did before, you can use this one. You can see what's going on. 3, for example. Okay, and you can see how it behaves in a cyclic test. So we are fine with this. Let's copy it. And let's make the one for the width direction. As I told you, I inverted the property. So the strong direction will be the width direction, actually, just to be consistent with the file that I sent you. But it is not a problem, actually, just an example. So width direction, same one, but we need to change some values. 0.0342. Same thing down here. Then the moment is the shear strength is 326 to power of 3. Same thing for the negative part, but with a minus sign. Then these parameters are the same, and all the others are the same. Perfect. So let's do a quick test. Okay, perfect. We're fine. So we have two uniaxial model for the shear in Y and Z direction. How do we include them in the column property? Now, first of all, we want to include them here, so we need to bring it up. So let's move them before the column property, just after the column, and the same for this one. Then I'm going to show you why. Perfect. Now we need to use the so-called section aggregator, because here we have a fiber cross-section, but we need to combine this one with these two uniaxial models. So let's go under physical properties and call add. Let's call it column aggregator. And then we go under section, because you can see the section aggregator is still a section. So we go under aggregator, and we say, okay, by default, you don't want to use a section. You can select 6 independent uniaxial models. Now, in this case, we have a cross-section, so use section tag, and you can choose any section. Now, in this case, we want to use the column fiber section. We don't want to input the torsion here, because the torsion has been already defined elastically in the fiber cross-section. So we just want the two shear, okay? And we want in Vy, the Y, and Vz, the Z direction. Perfect. So now we combined the fiber cross-section with the two transfer shear. So let's press OK. Once again, let me move the aggregator just before the column property so that I can go here, edit, and I can change it. Instead of putting in every gauge point directly the column fiber, now this time I put the column aggregator. Okay? So this is just the only change that I need. Let me press save, and I can run the analysis. So with just what this change, you can include the shear deformation and nonlinear shear behavior in your model. Let's wait some seconds. Perfect. So let's go to the post-processor. Let me reload the analysis. Okay. Now the first thing that you can see is that now you also have the shear response. Okay. In the Gauss points, because now we explicitly included the shear inside the integration points. Now let's go to the output. This one is pretty much the same. Let me show once again the strains. The behavior. Visually, it looks like the same. Now we just need to extract some response. Here, actually, you can see the shear failure in this column. So you may ask, why is this happening only in this column and not in the other? Well, this is another problem related to strain localization. Now, well before, there was a nice localization of bending. Why? Because now, in this kind of model, the curvature was linear. So a linear curvature means that the finite element method already knows that is this the Gauss point they should localize, because it's the one that during the entire analysis has the larger curvature. Unfortunately, for the shear strain, it is constant over the element. So each Gauss point has the same shear deformation. But then it has also the same shear stress. So what is the Gauss point they should localize? Basically, it is random. In this case, it happens to this one just because of some round of errors, but could have happened also in this point or this point. This is, as I told you, another problem of strain regularization. One option that we are probably thinking of implementing in STKO is to assign some random field. So like that, the shear response that the user assigns to the Gauss points will be randomly altered in each Gauss point, so that one of them will be weaker than the other. But this is another topic. So in any case, as you can see here, we have a difference. And now let me extract the stress, the displacement reaction response, so we compare it with the others. So reaction on node, stage number 2, displacement versus load multiplier. Next, node 25, and let's call it UF shear. Okay, so this is the response. Let me remove this graph because I want to put it here, add, so that we can compare it. Okay, so now as you can see here, the shear failure happened before the bending failure. And then you also had the bending failure at this point here. But as you can see, the response of the system now is well influenced by the shear behavior of the columns. Well, now I want to show you an extra problem. So in this case, we just finished with the model number 2. Well, actually, now I'm saving everything on the same model. It is the same, but in the file that I sent you, that you can find on the website, you have 4 different models. One was the basic, then only with the shear, and then the next 2 steps that we are going to talk about now. So let me show you one problem that we have in this kind of models, both without and with the shear. Let me create the Gauss point plot, like this one. And let's choose to visualize section force, yes, but I want to see the action force. Now, what I want to talk about is the problem of, let me go back here, is the problem of the effect of the rigid diaphragm on the fiber cross sections. Now let's see. You typically expect a beam to have a 0 axial stress or just a small axial stress. You don't expect it to have larger, very large axial stress, even larger than those on the columns. So let's see what's going on in step number 2. So here you have the major stresses, major axial stresses on the columns of the order of 2 kilonewtons each one. Now let's push it. At the end of the, let me go step number 10. This one is the end, this one, the end of the vertical analysis. So you have 20 kilonewtons each column. Then you start pushing it, and then you can see that the, what is it? Let me, I need to change it to this one, to the section force, yeah, but the beams. Now in the columns, you had a maximum of 2.2 to the power 4, so 20 kilonewtons. Here in the beams, things are growing. As you can see, you reach a peak of 1 to the power of 6, so it means 1,000 kilonewton. And it is something that you were not expecting on a beam. So let's see what's going on. Let me pick one Gauss point, and let's see how and when this axial force is increasing. So let's extract a chart data on Gauss point this time. Next. Let's choose all the time steps. I want to see both the initial time step, the vertical one, and the horizontal one. And I want to plot it against the time step ID, so it is linear. I want to see how the axial stress changes in time. And we choose it was the first one or the second one. Let me go back. because now we have two section forces. Why? One is for the beams and one is for the columns, because now the beams have only 3 components, or 4 components actually, while the columns have 6 components, including the shear. So it is section force number 1. So go here, extract on those point, every stages, and I want to plot section force P. Next, next, and let's call it axial force beams. Now we just take one, we just took one Gauss point, but it is the same because it is constant in every, it's almost constant in every point. Finish. So this is what's going. Actually, no, I need to plot it against the time step ID. So let me remove it. Let me do it once again on Gauss point. Yes, I'm at Gauss point. Stage 1 all stages against the time step ID, not against the pseudo time. Okay, perfect. So this is what's going on. So as you can see, if I zoom here, in the first 10 stages, it is growing. It is growing because the rigid diaphragm is already constraining the lateral expansion of the columns, but not that much. It arrives to 30 kilonewtons, 20 to 30. But then when you start pushing it, when it goes highly nonlinear behavior, basically you have the neutral axis of the beams are trying to go up, and then the beam would like to expand in order to meet a 0 normal stress. But the problem is that the rigid diaphragm is not allowing the beam to enlarge. In fact, the rigid diaphragm says that one of those components, for example, the displacement in the x direction, should be equal. So the beam cannot have a differential displacement in the x direction from one node to the other, meaning that the beam will develop an internal shear stress that can grow and will grow according to the level of nonlinearity in the beam. And here it is reaching very, very huge values. In this case, is 1,000 kilonewton, almost 100 times those that you are expecting on the columns of this model. So how you can solve this problem? Well, one way can be to keep the rigid diaphragm, but to release the actual continuity of the beams. And I will show you how you can do it in STKO. In particular, let me go to these points here. I will show you how to remove this problem using the hinged beam. So basically, in OpenC, you can just detach the beam from the columns and then apply a discontinuity in the x direction. But this means that you need to create for every beam 2 extra nodes and the 0 length connections. And this is very, very tedious. In STKO, you have this tool that can be used to create this kind of end releases. For example, it can be used to create rotational hinges, or in this case, the actual release. So how can I do this? So let me go back. Oh, let me save this one. Let me unlink it so you can see the difference with the new one. And also the shear, I want to unlink it. Okay, perfect. So let's go back. Let me save this model. Let me apply this change. So how do we create an hinged beam? So the first thing that we need to do is to create some support material. I need a stiff material. It's like in a penalty method. Here I need a very stiff material. Don't put a number which is too high, otherwise you will have a problem. It just has to be a couple of order of magnitudes higher than the stiffness, typical stiffness of the beams in this model. So you go under materials, uniaxial. You choose some standard, uniaxial, some standard uniaxial material, and we choose the elastic one. And let me see what is the value that I picked before. It was 1 to the power of 15. Okay. So this one, let's call it my stiff material. And then I need to create a soft material to represent the release. Now in this case, actually, I don't need it. I will put a 0, but you can choose to put some value that is in between 0 and the real stiffness of your rigid diaphragm. So let's call it soft material. On the model, as before, material uniaxial, some standard elastic material, and we put 0 here. If you don't want to put 0, you know that your your slab has a certain stiffness, you can put a number there. Okay, that's okay. So we have stiff, soft. Let me change the name. I made a mistake here. Let's call it just soft. It's easier to find. Okay. Now that we have these two, we are going to create a zero length material. Let's call it zero length for continuity. A zero length for continuity means actually a complete connection in every degrees of freedom. So I go under under special purpose. I go under zero length material, and I choose 3D and 6 degrees of freedom. And I want to assign a spring to every degree of freedom, and in every case I want to use the stiff material. Then I will explain you why. But in this case, this is a very stiff zero length, so basically it is a continuity, okay? Then I will show you why I'm doing this. Then I do the same, but I call it zero length axial release. So it will be the same, but in material one, you can either choose not to put it, so it will be completely zero, or you can use the material model for the soft model. In this case, it is zero, but for example, you can change the value. So I typically prefer to do this. So it will be stiff everywhere. Actually, I made a mistake here. Let me make it stiff, 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 and then soft here. Let me check that here I didn't make the same mistake. Yes, I did a mistake. So stiff. This is stiff everywhere, while this one is soft only in the axial direction. Okay, so you may ask, why are you doing this? Because next to this step, we have the hinged beam property. Basically, this one is not an element that is available in OpenSys. It's just an automatism of STKO. It basically allows you to create beam with hinges at the ends without splitting your model. So you can keep your model continuous, and STKO, instead of creating one element between the two original nodes, will create two extra nodes. We put the element in the middle, and we create the end hinges. So let me choose hinged beam. And here you need to choose the property for the beam in the middle, and you choose the beam property that you had before, and then the zero length that you want in the first and in the second edge, in the second node. Let's put one node, so for example, the first one to be continuous, and the second one to be released. Don't do the mistake to release both of them, otherwise your system will be singular, because of course then the beam will be released in both sides. So let's release just one node. Let's press OK. Okay. Now, since we choose to keep the first node continuous and the second released, we need to do a check. The order of the nodes will follow the order of the orientation of the local axis. So here, for example, the first node is this one, and this one is the last node. In this case, it is the same. Here, it is going from this side to this side, but in this beam is the opposite. Now we want to make sure that they are aligned in the same direction. So how can I do this? I can use the reverse command. You can click the reverse command, then choose the geometry whose local axis should be reversed, and I click this one, right click, and as you can see, it is rotated according to this one. So those two point along the positive y direction, and these two along the positive x direction. So let me go under property. I select all the beams. Okay, perfect. This beam, this beam, this beam, this beam, and I drag and drop this time the hinged beam property. Okay, perfect. Now, as you can see, the hinged beam property has this kind of representation. It puts a gap here just to let you know that you have an hinge there. Now we need to do the same for the element, because now we cannot use a simple element, we need to use an hinged beam element. So once again, we go here, and we call it hinged beam element. We go under model, beam column, now it's actually under special purpose, hinged beam. Now in this case, we need to choose an element for the interior beam and a zero length element. But actually, we forgot to create the zero length element, so we do it now. We go under element. We create a zero length element and go under zero length, and we choose one of the formulation. We just want the standard zero length. We make it 3D, and we don't need to put anything else. So this is fine. This is our zero length element. Now we can create the compound element, so that basically groups the standard beam element with the zero length into one. So let's call it hinge beam. Go under model, special purpose, hinge beam. Here we choose the beam element, so the one that we assigned before. And then in both the I and J nodes, we choose the same zero length. Now here we don't have to do any difference, oops, because the difference is already made in the physical property. Here we just need the finite element, which can be the same for in both ends. So okay, now we just need to select these beams. Oops, sorry, actually not those ones, the beam one, not the columns. So all the beams, and we can drag and drop also this one. So let me make sure I assign them perfectly. Okay, so now we created the actual release. If I didn't any mistake, it should be fine. Let me just go under mesh. It is fine, let me remesh it, but there is no need. I save it, and I run the analysis again. Oops. Okay, it's going. Now let's see what happens when you release the actual direction. Perfect. Let's go back to the post-processor, and let me first save this model. Okay, the post-processor, let me save this one as well, and I will reload the output. Okay, so now this one will change. Let me see the fibers. They're pretty much the same. Now you cannot see the difference right now, but let me show you the difference in a different way, with a different plot, with a surface color map, and I switch off the beam extrusion, and I show the nodes. Now let's see here. Basically, I created a release in these two ends. So let me increase the deformation scale by 10. As you can see now, these two nodes are actually, this node is rolling over this one. So it is released from that one in the x direction only. So as you can see, as the analysis goes on, the beam would like to enlarge to meet the zero normal stress constraint. But to do this, it needs to enlarge to represent the opening of the crack. Okay? And now we can make sure that we don't have any normal force here. So we go back to the section plot. We are here, section 1, P. As you can see now, the value of P is extremely small in this direction. Something more in this direction, we didn't check it, but in this direction, you can see it is approximate to 0. So let me select one of them. And let me do it again. So all the stages against the time step AD using the normal stress. Next, next. Actual force being released. Okay, so this, as you can see, they are 0, just small errors, but you can reduce them by reducing the tolerance. And let me put it here. And so as you can see, we reduce all the error to 0 basically, except from those small errors, but you can calibrate them using a smaller test increment, a smaller test tolerance. So in this case, this is a quite effective way of reducing this error, because this one actually is giving you unexpected results. So let's see what happens with respect to the total displacement-based shear response. So let me go back to this one. Let me select this node, and let me extract again the displacement versus base shear. So this one, this time we only want Stage number 2 against the pseudo time step and displacement in walking next direction. Next, next. And we call it UF release. Okay, and let's put it upon this one so we can compare them. So as you can see, the response changes a lot. Basically, you have a smaller strength, which is expected because you have in the beams less axial stress and more ductility. Okay. So keep in mind to take care of this problem because the normal stresses on the beams can become quite high when you have the rigid diaphragm. So here we reach the third point of our presentation. Now we are going to add the last level of detail, which is the nonlinear model for the joint. Okay, so let me go back. We talked about regularization, the shear, and then the joint. So for the joint, we're going to use this formulation called the Shear model. So basically, we are going to have, if we have two beams and two columns here, we're going to join, we're going to duplicate the node of the vertex here of the node. Between these two duplicated nodes, which are actually coinciding, we will create a zero-length element with a spring in each of the direction of the coinciding beams. And then we will create rigid links to represent the panel zone. And then here we have some formula to compute the stress-strain relationship. Actually, it will be a moment rotation relationship, but the rotation of the Shear model can be related to the plane shear deformation of the joint. Okay, so let me go back here. Let me save this one. But before saving everything, I want to unlink these charts, otherwise they will be updated later on. So that we will apply also we'll compare it also with the effect of the joint. So let's go back to our original model. Oh, so just to give you a summary up to now, the files that I sent you, the first one is the one with only nonlinearity in beams and columns, without even the shear, just with the finer mesh, so 3 elements per member. Then the second model is when I added the shear. The third model is this one, so when I added the actual release. And then the fourth model corresponds to the addition of the joints. I just realized that the model that I uploaded probably has a mistake. In fact, you cannot load it probably if you already tested it. But I will upload an updated version as soon as I finish this one. So you will find it on our website. Okay, so let me switch off the local axis. We don't need it now. So what we need to do is to create joints. To create these joints, we need to do a small modification to this model. We first need to cut the beams to create the rigid panel effect here in these zones. I have to say now that the construction of the node is not automatic, so you need to do something by hand. So let me see how we can do it. So let me go back to the geometry module, and I want to create 2 nodes. One node here, and again, one node here, okay? So we have the original geometry, the master node, and these 2 extra nodes. I want to select them, and you can move them along the x direction. Select 1, 2, right click, and move it along the x direction, but keeping the orthogonal constraint. So we move it along the line, and we have to move it of half the width of the column, which is 150. Okay, so if you compare it to the property, you can see, well, actually it's in the other direction. Okay, so it was 2.5. Let me go back to geometry. Let me move them again. So select these, and these. Let me move it again of other 100 millimeters. Okay, so this is fine. This is exactly 25 like here. Now let me go back to geometry, and I do the same on the other direction. So first of all, let me mirror this one Let me create a copy from here, here. I want to mirror them on this other side, so let me create a mirror plane like here. So we have them here now, and we do the same on the other direction. So let me create another 2 points, this one and this one. Now I select them, and I move them of 150 millimeters. And once again, I'm going to mirror them to create the same nodes on the other side. Right click and select the mirror plane from here to here. Perfect. Now we have all of them. Now, how we can cut these points? Now we can select all the geometry, so this one plus all the other nodes. We can just do like this, but without the interaction and the master node. And we can use, let me move this one, sorry. We can use the merge command. Merge basically tries to perform a Boolean operation, joining everything that is coinciding, eventually performing intersection. So let's press OK, and now we have one master node and one merge geometry with all these cuts. Okay. Now what we need to do is to remove these pieces here because they will be actually rigid links, so we don't need a geometry for them. So switch off the selection of the entire geometry, so we can select the sub-geometries, and we can select these edges. Same here. And these other edges in this direction. And here. When you have all of them selected, press cancel, so they will be removed. So don't worry about the condition and the physical properties, they are still assigned, okay? Both physical properties and conditions, so don't worry about them. Let's go back to the geometry. So now we created this connection between the beams and the columns. Now, as I said, we need to create a copy of the node. We need to create another node, which is actually coinciding. But working with coinciding geometries can be confusing. So I will first create 4 nodes for the joints. I will move them along the z direction. We will work on them, and then I will move them back to the columns. Okay. So let me create 4 nodes. Here, 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 and here. Okay. Now let me select these last 4 nodes. So select, select, select. Now for the ease of selection, I can create a compound. A compound is basically a group. Okay, so I can select them all at once. And I want to move them along the z direction of a random amount, because then I will move them back. So there is no problem here. Okay. So these nodes up here will be the duplicated nodes of the joint. So what we want to do is to attach the beams rigidly to these nodes, and then these nodes to the original node of the column with the nonlinear spring. Okay. So how do you do this? We need to create an interaction. So let me call add. Let me call it interaction rigid links. Press OK. So we first need to select the masters, and I want to use these duplicated nodes as the masters. Okay. Right click, and then select the slaves, and I will select all the beam nodes as the slaves. Now I can do it all at once because basically the algorithm that we use to join master and slaves basically attaches every slave to the nearest master. That's why I can do it like this. Otherwise, I need to do them one by one. So right click, and as you can see, every slave is connected to the nearest master. So these ones are basically the interaction that are going to represent the rigid links between the beams and the duplicated node of the beam column joint. Now we need an extra interaction that connects the duplicated node with the column node, and in this case we are not going to use a rigid link but a zero length. Okay, so let me create another interaction, and let's call it interaction joint, and we select all these nodes as masters. Perfect, right click, and all the column nodes as slaves. This one and this one. Right click, and now as you can see, I created all these small interactions here. Okay, perfect. Now we're going to assign the physical properties and the conditions to them. So the first thing that we want to do is to go under condition to create the rigid body constraint between these ones. So let's go in condition, add, let's call it joint rigid link. We go under model, constraint, multi-point constraint, and we choose the rigid link. Rigid link, we are in 3D, and we want to use the beam formulation, not the bar. The beam formulation means I want to join everything, displacement and rotation, and it will act as a rigid body. Okay, now we need to select the target, which is this geometry. Now, since I created them with just one command, I can click just on one of them, and I will select all of them. So let's press OK, and here I have the assignment of this constraint. And as I did before, you don't need only to create the condition, you also need to assign them on the analysis step. So let me edit the add constraint here, where I add only the single rigid diaphragm constraint, and I'm going to add another multi-point constraint, which is the last one that we created, which is the rigid joint link. So this one will be part of the analysis as well. So we created now the rigid links. Now we need to create the nonlinear joint here, the nonlinear spring. So how do I do this? Pretty much as I did for the end releases. So I need another zero length material. Not another zero length element because it is already there. I need another zero length material. So I already have a stiff material. I have a soft material. Now I need a material for the joint in the two rotational components along the y and along the x direction. Now keep in mind that this interaction here has a local axis which is global. So you have to create rigid nonlinear springs along the global x and y directions. Okay, so let me create another physical property which is going to be equal for both x and y direction for simplicity. And in this case, we are using this formulation. Let me go back to the node. So we're going to use a pinching for material that allows us to assign these 3 points plus a residual. We're following these equations. So let me go under, let me call it joint linear model. We go under material, uniaxial, and we choose other uniaxial material, pinching 4. And now let me see the numbers of this one. Okay, so we have here the coordinates of the point. We don't need the optional values because it will be symmetric in the positive and negative direction. Here we have 156,380. Then we have 248,420. The third point, 261.500. Not 0.500. And then the last point, which is the residual one, which is 112,440. And then the corresponding strain components, 0.0004. Then we have 0.0017 and 0.0049 and 0.0393. Now we don't need the optional component because it will be symmetric. Let me put some values here: 0.16, 0.23, minus 0.22, 0.85. Here are some values for the cyclic behavior. It is not so important, but we need to fill all of that. Then we have 0, 0.9, the GK limit 0.96 and 0.38. Let's go back to the GD3, which is 0.34. Then we have 0.96 GD96. Then we have one extra value here in GE, which is 100. And the damage type will be cycle. Okay, let's test it. Let's go and see what's going on if we put everything correctly. 0.001 should be fine. Let me see. Okay, let me push it a little bit more. So here you have the first point, the cracking, the pre-peak, the peak, and then the softening you should have here. Okay, let me push it a little bit more. Okay, perfect. So this is the behavior we're going to give to the joint in both X and Y direction. Then of course you may have different behaviors, but here for the sake of simplicity we use the same one. So here we have the joint nonlinear model. Now we need to create a zero length for this one. So let's go to physical property, add, and let's call it zero length joint. Similar to the other one, it will have a special purpose, zero length material, 3D, 6 degrees of freedom. We're going to use all of them. Now they're going to be all of them stiff, so rigidly connected to the original node, except from the two in plane rotation, out of plane rotation. So stiff, stiff, stiff in the three translations, then stiff in the in plane rotation, and then the nonlinear joint in rotation about the x and y axis. Okay, joint nonlinear, perfect. This is okay. So we're going to select these interactions here, and we can drag and drop the zero length for the joint. And at the same time, we select them, and we drag and drop the zero length element that we already created for the hinged beam. As I said, it is still a zero length element, so we don't need to create another one. That will be fine. Now that we assigned everything, we can move these nodes back to their original position. And the connection will be collapsed as well. But of course, we do this because now we don't need to select it anymore, so we can move it away. So let's go under. Let me go back here to move. Let me select all those nodes. Okay. I think I have I have a window on the other side. Let me just go back to two screens, just a second, because I cannot see it. I can see this one. I can see this one. I cannot see the one for the translation because typically I work with two monitors, but now it is giving me a problem. So let me just go back to two monitors, and I will be back soon. A second. Like STKO, when I click move, here, there should be a window, but for some reason it goes back to only one. But anyway, now the remote desktop is giving me a problem. I cannot see the window. But when you click move, actually there should be a window that appears saying that if you want to copy or just rotate or just move. It should be on the second screen, but I'm having a problem with that. So let me try to do it again. Okay. Well, if I can do it, doesn't care, you should see on your screen. So move. Let's move. I still cannot see it. Well, probably it's even worse. They moved it away. Doesn't matter. I will keep it aside, and then in your case you can move it. But anyway, you can when you open your model, you can see it. It is collapsed. So okay, keep modifications. Okay. Now it doesn't matter if it is offside like here. It's not a huge problem. But if you use the move command, it can go back to the original direction. There is something I can do actually because I moved it too far away due to the remote desktop, and it is giving me a problem. But anyway, this one is fine. We added a new element. I will just need to remesh the element. So build mesh, this is fine. And let's run the analysis. Okay, in the meantime, I will try to resolve the problem given by the reg editor. Okay, just a second. Is the command copy? Where is it? But I should find escape parameters, transformer copy dialog. Okay, let me remove it. Okay, here we are having convergence problems. Then we'll try to change something. Probably it's due to the position. Let me try to move them back. So move. I still cannot see it. But anyway, let's see what's going on here. So let me reload file. Okay. And let me run. Let me see where it arrived. So probably it was too weak, the joint, probably because I couldn't move them down. But anyway, you should be able to see the dialog where you can move the node. So let me go back here to the joint behavior. Let me see what happened to the joint. So let me select this one. Let's extract again the displacement versus reaction. Okay, stage number 2, next. And this is UF joint. Finish. Okay, so basically we had a convergence problem up here. Let me see where it arrived. Join node. Okay, basically we have, well, probably it was too weak in joint. Okay, I have some mistake in the input parameter, but then you have them on the presentation. Basically should go slightly down like this one, where I can increase number of interaction, but the idea is the same. The only thing that you should do to complete this one, now probably have to switch off STKO and reopen it probably, but you should be able to see an editor like this one that says if you want to translate or copy, as soon as you click on the move command, I need to switch off I need to switch off the desktop remote now, but I cannot do it. And so you can move these nodes down to the columns so that you don't have this extra gap, and you can run the analysis. So basically now we have everything. So I think we can go with the questions if you have any. Well, of course you can see the visualization, like here I'm visualizing the fibers, but let's say you want to see the results on the node. How do you see the results on the node? This is a zero-length element, so you can ask for a result on the node, going on the recorder, edit, and then you can choose on element recorder the material stress and strain, because material stress and strain is used both to obtain the results on the solid Gauss points or in the Gauss points of the zero-length elements. They also respond to this keyword, material dot stress or strain. So let me run again the analysis. Okay, run it, and let's see what's going on in the nodes.
Here we have convergence problem. Okay, it's not a problem now. We don't need to solve it now. Let me reload this one. Okay, this is the behavior of the joint. Now let's say we want to visualize what's going on in the joints. So we go to material strain and material stress, and as you can see now, we have these dots on the joint. But probably here something happened, or probably I forgot to assign the joint because here I cannot see anything. So probably here I assigned the wrong direction, but this is not important. So here you can see stresses and strain. Let's say you want to see what's going on in a node. It should be this one. So let me extract on Gauss point. Next, stage number 2, against the result. So we choose material strain here and material stress here. And we should see the fifth component, which is along the y-axis. So the fifth component should be the shear of the node along the x direction, if I don't get it wrong. Well, here it is still elastic, so probably it's not this one. Let me see if it is the x direction. Oh, probably it's not this one. Actually, this one I think is one of the zero length. Oh no, that's why. That's why I need to select this one. Yeah, I picked the wrong one. This one is actually the results coming from the zero length of the end release. That's why it is elastic and so stiff. It is this one that they need to visualize. Gauss points, stage number 2, against the result, material strain and material stress. Fifth component. It should be this one. Okay, so this is the behavior of the joint. Okay. So let's say for now it is all. So as you can see, then we had some convergence problem due to reaching a very large unloading here. But you can play with the convergency parameters and tolerance. I think that if you move the corner nodes down, you won't have this problem because I didn't have this problem on the reference model that I was using. I will try to solve this problem now. Okay, so I think that for now is everything. So if you have any question, we can have other 10 minutes of questions. So please go ahead with the questions if you have any. Is it everything clear? If you have some doubts, please ask me a question and we'll try to answer. I think there is no question. So let me stop sharing. Number of integration points affect the strain, right? Yes. So let me go back. The number of integration points is not actually affecting the strains. Is that when you use a force-based beam element, the strain will localize into just one Gauss point, because in a force-based element, what you enforce to be continuous is the stress, and then you iteratively find the strains. So it's the opposite of the displacement-based element. In this way, two neighbor Gauss points do not need to have the same continuous strain. So one can localize. On the opposite, if you use a displacement-based element, the strains of the Gauss point comes from the compatibility with the displacement, so they will be continuous. And instead, you will have a different non-continuous stresses along the beam. So let me see. Are you planning to make an automatic tool to define the joint? Yes, of course. Of course, we will do it because we have seen that constructing the joints by hand takes a lot of time and it is very error prone. Like for example, in this case, probably I missed some connection between one node and the other. While I was doing it 10 minutes ago, there was no problem. Of course, we are going to do it, and I think we are actually evaluating the best way to define the joints. Like we tried this Shear model, then we will try some other formulation, and we will see what to implement. But of course, yes, we're going to implement it in automatic because it is not feasible to do it by hand, especially on a large building. It takes minutes on the small building, it will take hours on a regular building. So it will be definitely automatic. Actually, it will be ready, I think, in the next months, in the near future. So if there is any other question. What about loads? I'm used to SAP that use a floor load. Any plan? We are creating a floor load actually now. So it will be there, I think, in the next week or in the next 2 weeks. We're actually doing it right now. It will work for 4-node and 3-node surfaces. And for general surfaces, we will create some kind of triangulation. So yeah, it will be like more like the the floor load used in Midas Gen, which is similar to the SAP one, but I think more handy. If you have ever seen Midas Gen, it is a nice way to define floor loads. So yes, it will be ready in a couple of weeks. Yeah, we're actually working a lot on this kind of automatisms because they really help you to create model faster and without chances to do errors. Because repeating these operations each and every time is very error prone. Can we ask for additional courses for special topics? Of course. We have a forum online. So if you want to ask for special courses, if you want to request a special training, of course you can write on the forum and we will try to schedule those webinars as soon as possible. So please, we need this kind of feedback, of course. So I think if there is no other question, we can stop the webinar. Okay, so thank you to everyone for joining. And the next webinar will be, I think, within 20 days. We will do the same models as of now, but not with the distributed approach, but with the lumped approach. Following, there will be example, the next webinar after the lumped approach will be the soil structure interaction. So people interested in geotechnics can join the next one. So thank you so much and see you on the next webinar. Bye.